So far we have talked about the logistic map as a deterministic function that can create a chaotic situation. Uh, we have many examples of this system in the real world, such as climate change, stock market, financial markets, or many other markets that can be modeled using this approach. Which in some cases they have a single or point attractor regime. In some cases they have periodical attractor regimes with a different number of periods, and in some cases they have strange attractor, which is chaotic attractor. And this is a very profound finding that we can delve deeper just to enhance our understanding of the dynamisms of these systems. So the first thing to consider in these kind of systems is the sensitivity to initial conditions, that also known as butterfly effect, that I just showed you, that is making these chaotic systems impossible to predict. And in order to again understand the mechanism behind that, consider these two important definitions. One is the stable development, which is the result of negative or self-correcting feedback, which keeping the system in the basin of the attraction. That's almost equilibrium, because equilibrium is a single state, so we cannot really consider a thermal equilibrium. It's a temporary equilibrium, which is another name for the attractor, and that can be a single point attractor or a periodical attractor. But then the changes in this system, because of the existence of the positive feedback loop, or the basically destabilizing feedback loop, result in disturbing the system to the state of far away from equilibrium, and taking the system to the edge of the chaos. And in the chaos onsets, this positive feedback loop pushes the system to the state that suddenly it has no single or periodical attractor. The system's new attractor is a dynamic attractor or strange attractor, which from the single point attractor perspective, it basically has no attractor. And as a result, system is in chaos and it's not any more predictable. And this is a very well-established area in the mathematics known as dynamical systems, that these attractors can be studied. A good example of this is the Lorentz butterfly attractor with 2 points of attraction that you can see in this image below. In fact, that butterfly effect is coming from this attraction, which forms a geometric attraction, two periodical geometric attraction in this case. But also the chaotic systems can be evolved from the same system we just showed how it is possible. Now, as the last part of this video, I want to show you how we can map this relationship between the attractor and the R in the model. So consider the point of attraction that we have talked about already so far. So let's say, let me just write down the formula again up here. So we have x sub t plus 1 is equal to r times x sub t minus x sub t square, and that's our logistic formula that we use. Now, for every value of r, we can create a new map that is called bifurcation, and bifurcation basically maps r on the x-axis to x on the y-axis. And it works like this. So if we start with the value of 2 on the R, let's say this is the value of 2, we know that 0.5 is the attractor. And if we move to the next value, 2.01, we are going to see that a new attractor is happening, and this continues like this up until the point I believe it's around something like 3, that we see that this bifurcation happens, and then a little bit after that a new one happens, and then it continues like that, and the new one happens. And this is what called bifurcation in the logistic map, or logistic bifurcation, logistic map bifurcation. Now, why is this important? So let me show you an example of logistic map bifurcation. And this is the exactly the bifurcation for our example of the logistic map. And as you can see, it starts with a single point attraction, fixed point attraction. So the entire part here, let me bring the laser point. So the entire, this parts from 2.4, R of 2.4, up until this value of around 3 point something, maybe 3.05, we have a single point attractive regime. The value is changing. It's passing 0.6. It's reaching to 0.7. So the value is different, but at any state of R value, we have a single point attractor. But after that 3.05, we see a 2 periodic attraction. This is the periodical attractive regime. So the attractor regime changed from a single point fixed point attractor to a periodic attractor. And this continues to 3.4 something, which becomes period of 4, it continues period of 8, continues period of, and it continues like that. And after 3.55, or something close to that, which is the onset of chaos. And after that, we can see strange attractors, which is not anymore any of the previous ones. Now, we keep saying that this is not predictable. The state of chaos is not predictable. But there are some universal characteristics that can be predicted. In fact, if you look at this distance from this point to this point and compare it to the distance from this point to this point, and then compare that from distance from this point to this point, basically you see that that distance is shrinking. In fact, Feigenbaum has calculated precisely, empirically and theoretically, mathematically proved that this is like 4.66 something times every point next attractor regime is 4.66 times shorter than the previous one, and that is universal. So no matter of where in this bifurcation map we stand, the next attractor regime is 4.66 times shorter than the previous one, and that's universal. So yes, we cannot predict the exact state of the chaotic system, but we can predict some universal characteristics of these systems. Another very interesting point about this bifurcation map is that it is fractal nature, meaning that it's a self-similar system. We are going to learn about this more in fractals next week, but the week after next. But for now, look at this shape that is coming and then turning to this bifurcation is more or less the same thing happening down here. And then you can see down there. So in fact, if I zoom in, and by the way, a good example of this systems is the magnetic field. A physical example of that is the magnetic field. Now, if I zoom in, see, this is a similar shape to the previous one. My image is low quality, so I cannot zoom in further. But if we have a higher quality and zoom in this part or this part or this part of the section, it's going to be self-similar to the previous stage, and this can continue indefinitely because this is a fractal system, and this closely relates fractal systems to chaotic systems, and studying chaotic systems, in fact, with fractal systems.